Hello, I'm Jason and welcome to this section of the Calculus 1 Derivative Help Tutor. This section we're going to cover implicit differentiation. It's a topic that a lot of students have problems with, but I promise you if you learn it in the right way, implicit differentiation is not a big deal. And I plan to show that to you and prove that to you by the end of this section and the end of the next section where we're going to work a lot of problems here. So don't forget what we've been doing up to this point. We've been taking derivatives where the function was given to you ahead of time, right? F of x is equal to something, some function of x. And all of the techniques you've learned have been geared towards you finding that derivative. But in all of the functions that we've given you, every single one of them, f of x is on one side and everything else that the function is equal to is on the other side. So to kind of nail this and to kind of bring it home for you, it's been something like this. F of x is equal to x squared. Or if you want to write it in a simpler term, you might say y is equal to x squared. This is a function, right? So this variable y we say is equal to x squared. But notice that y is completely solved for on this side of the equal sign. So when we take a derivative of this guy, what we're really doing is taking the derivative of both sides of this equal sign. So if we're going to write it in terms of this fractional notation, you would say dy dx is equal to 2x. And that's what we've basically have done earlier in this course, but notice what you're doing. You really haven't sort of explicitly told you this, but you're taking the derivative of both sides of this equal sign. On the right-hand side is just 2x, that's the rule of differentiation that we've given you. On the left-hand side, you're taking the derivative of this variable y, but you don't know anything about y. This is very important. You don't know anything about y. You don't know, well, you know it's equal to x squared, but you don't know anything else. So basically, when you take the derivative of y, you're just writing down what you're trying to find the answer to, the derivative of y with respect to x. So on the left-hand side of the equal sign, this y becomes dy dx. On the right-hand side of the equal sign, you just take the derivative. And you can do that because y is totally solved for over here, and everything on the other side of the equal sign, you're just using the rules of differentiation that we have. So this is what we have done so far. But let's compare that to a different problem that isn't quite so easy. What if I gave you, and this will be our first problem that we're going to end up solving, by the way. What if I gave you 3y squared is equal to negative 2x fourth? And I said, hey, I want you to find dy dx. How would you do that? Well, you have never been given a function or a problem like this. In all of the problems that we've given you, we've always given you the variable, the dependent variable is equal to some function of the independent variable on the right-hand side. Everything's been solved for, so y is by itself. But here that's not the case. We have 3y squared is equal to something on the right-hand side. So this equation is said to be implicitly defined. This is what we call an explicit equation because it's explicit because we know that y is equal to something, right? So therefore the derivative of y is equal to something, and that's what we have done all this time. Here, this is what we call implicit. What does the word implicit mean to you? It means that when someone implies something, they're not really saying it so overtly. They're kind of hinting a little bit. They're giving you enough clues to figure it out, but they're not really just telling you, right? So that's why this is explicitly telling you what y is equal to. This gives you all the information with regard to how y and x are joined and how they're related to one another, but it's not explicit. It's implicit because I'm sort of telling you kind of in a roundabout way how y is related to x, but I'm not explicitly telling you by solving for y. So one way to find this derivative would be to solve for y, right? I could divide by 3, and then I have y squared, so I'm going to have to take the square root of both sides. And anytime you take the square root of both sides, you're going to have to put plus minus, right? So I'm going to end up having a plus and a minus radical with all this stuff on the right-hand side. Then I can take those derivatives and I can get the answer. So it's possible to actually solve this equation for y. But just as an aside, what if it wasn't quite so easy? What if it were sine of y is equal to x squared? How would you take the derivative of that one? You can't really solve for y there easily at all. I mean, you could take the inverse sine, but then how do you take the derivative of the inverse sine? You haven't even learned that yet. So this is all kinds of problems we're going to learn how to take these derivatives whenever the both variables are wrapped up on both sides of the equal sign. And the way that you take a derivative of an implicitly defined function like this is by using implicit differentiation. That's why it's called implicit differentiation. So it means you take the derivative of both sides with the technique that I'm going to show you in a minute, but it's done in situations when you don't have y already solved for. All right, so this particular equation, we probably could mess around with it and make put y solved for itself on one side, but that's sort of besides the point. We want to start with an easy problem, show you how to do it, but I promise you in a few minutes I'm going to show you problems that you cannot solve for y easily at all. What if I put a logarithm around here? What if I put a tangent around here? Then you wouldn't be able to solve for y. So just work with me here and we'll see. What I'm going to do is get all the way down to the answer, and then we're going to have to talk about it a lot to show you why it works. But once you know the technique, it's quite simple. All right? What we're going to do, much like in this case, we took the derivative of both sides. Derivative of y is dy dx. Derivative of this is 2x. So that's what we're going to do here. We're going to take the derivative of the left and the derivative of the right with respect to x. And then ultimately we want to find this derivative dy dx. So when it's done this way, you take the derivative of this side just like you always have. How would you take the derivative of this if this were an x here? You would say 3 times 2 is 6. So you would say 6y to the first power. You would subtract 1 off that exponent, right? But you don't know how y relates to x. So you've taken sort of this first order thing here. 2 times 3 is 6. Subtract 1 off the exponent. But you don't know how y relates to x. So you have to multiply by dy dx. And you're thinking to yourself, what's he talking about? This doesn't make any sense. Just bear with me. Let's get to the end of the problem. I'll come back around and make sure you understand it. On the right-hand side, this is what you've been seeing all along. So you just take derivatives of this just like you always have. 2 times 4 is 8. You got a negative. Negative 8x to the 5th power. Whoops, to the 3rd power, because we subtract 1 off of the exponent. So what we're seeking to find is dy dx. So we divide both sides by 6y. So what we'll have is dy dx is equal to, when we divide by here, we'll have negative 8x cubed over 6y. And so ultimately our final answer is going to be dy dx is equal to, when we simplify this fraction, we'll get negative 4x cubed over 3y. This is the final answer using implicit differentiation. The derivative of y with respect to x is equal to negative 4x cubed over 3y. Now, there's a ton of stuff that I really want to talk about in this to make sure you understand. So let's go and do that now, and then we'll work a lot of problems. What we have here is an implicitly defined equation. We do not know how y is a function of x explicitly. We are not given that. We can try to solve for it, but like I'm trying to tell you, in future problems, you won't even be able to solve for it. So just forget about trying to solve for it for right now. We do not know how y depends exactly on x, but we do have a relation that tells us how the two are related. We have an equal sign here. We know that this quantity is equal to this, but we just haven't solved for y. So we take the derivative of both sides of the equation in the hope that we can eventually solve for dy dx. And we can in almost all cases. So forget about this. On the right-hand side, it's exactly what you've been doing the whole time up to this point in calculus. I mean, 2x to the 4th power. We just multiply x, subtract 1 off the exponent, bada boom, you're done on that side. The only thing that it becomes different is the other side, because you have this y, and I'm telling you now that you're going to end up taking derivative of this y, right, as well. So the rule of thumb is you take the derivative exactly according to the rules of differentiation of everything else. 3 times 2 is 6, y, subtract 1 off. No matter what you have over here, this function of y, you take the derivative exactly like you always do. But you have to multiply what you get by dy dx. This is the magic that makes this problem solvable. Because ultimately, you're taking the derivative of the left-hand side. But once you do the first part, you don't yet know how y depends on x, so you have to stick that in here. And to make this a little bit more clear as to why we're doing this multiplication, let me go ahead and try to do a little bubble or something around here to kind of pull it down here. I want to make sure you really understand. This is the chain rule. In other words, I didn't tell you ahead of time, what you're doing here is you're applying the chain rule to this problem. How do you do, think back for a second, let me change colors here. How do you do sine x squared? How do you take the derivative of sine x squared? Well, you know it's the chain rule. You've got an outer function and an inner function, right? So what you do is you take the derivative of the outer function, the sine function, which is cosine x squared, and then you take the derivative of the inside, which is 2x. So it's 2x cosine x squared. That's how you use the chain rule to find this. What you're doing is the chain rule here. This function, the outer function, so to speak, is the whole thing. So you take the derivative of it, leaving everything intact, so it's 6y, right? And then you have to multiply by the derivative of the inside. Just like we're doing here, the derivative of the inside is 2x. In this case, the inside function is just y. We don't know how y depends on x. That's what we're trying to find. So once we do the outer function, the 3y squared giving us 6y as our derivative, in order to make it complete, we have to multiply by how the inner function, which is this y, which we have no idea what it is, how it depends on x. So we just, since we can't actually do it, in this case we can take that derivative because we know the derivative of x squared is 2x. Here, the derivative of y is simply dy dx, so we multiply by dy dx. All right, let me say that one more time. The outer function is the whole thing. We take that derivative, we have to multiply by the derivative of the inside, which in this case is just the variable y. The derivative of that is dy dx. That's why we leave it written this way. And that allows us to solve this problem, okay? Now, the other thing I want to say, hopefully I won't confuse you too much, but when you do this side on this side, you're really doing the same thing. You've always been doing the same thing. I just never told you. Because when you took this derivative on the right-hand side, what you were doing is taking the outer function, so to speak, was 2 times 4 gives you the 8, x to the third power, subtracting 1 off. But what you really have always been doing up to this point is you've been doing it, and then you've been multiplying by the derivative of the inner guy, which is x, and the derivative of that is dx with respect to x. And this is just a fraction that's equal to effectively 1. So you never see dx running around your derivatives anywhere because I've taught you, and your book teaches you never to really even worry about it. But it's important to kind of bring it up, I think, a little bit at a larger picture now so that you understand what the calculus is doing. You're doing the same thing to both sides of the equation. You're saying the derivative of this is 2 times 4 is 8, x to the third power, times how this variable, the inner function, varies with respect to x. But it itself is equal to x. So dx, it just disappears. You never see it anywhere in any of your derivatives because it drops out to 1. So when we do the same thing to the left-hand side, 2 times 3 is 6, y to the first power, times how this variable changes with respect to x, obviously it's not going to disappear, it's going to be there. Okay? So I think I just wanted to make sure and tell you that the technique is going to become mechanical and easy as we do more problems. But I want to let you know that's what you're doing. You're using the chain rule here. So we find this guy, we solve for dy dx, we get an answer. Now notice how this differs from a regular answer. dy dx is equal to this quantity that we've calculated over here, and this quantity has x's in it and it also has y's in it. That's something new. If you go back and look at all the other derivatives we've learned, x squared, whatever, it doesn't matter. We've always had, since we had y on one side of the equal sign, then everything else is x's on the other side. Our derivatives only involve x, or t, or whatever variable we're dealing with. This derivative involves both variables. The reason it involves both variables is because our original equation was not explicitly defined for y. And so it's very common, in fact, you'll always see x's and y's in all of your answers, so don't get spooked by that. What it means is that if I want to find the derivative of y with respect to x at a given point, I need to know the x value and the corresponding y value that satisfy my original equation, my original function. I need to know x and y because the original guy that I started with did not explicitly define how y was equal to x and all the x's on the other hand side of the equals. So you do it the same way. If you want to find a numerical value of the slope of the original curve, you can still do it. It's just that you have to know x and y to plug in there to get the answer. Whereas if you had a really simple equation like y is equal to x squared, you take the derivative and then everything is on each side of the equal sign, nice and neat, and then when you find the derivative at a given point, you just plug in your value of x, and there you go, you get your answer. Here you're going to have to supply an x and a y value. That's because this function is not explicitly defined. All right, that was a little bit of theory. I usually don't do too much theory in calculus because, it's nice and it's cute and it's important, but really what's more important, I think, is the mechanical, just get in there and solve these problems, and then you can get your confidence up. Whenever you do it enough, you'll start to understand how the things sort of fit together. But I felt that it was important in this case to at least show you what's happening, and in fact, implicit differentiation is simply the chain rule. So let's go ahead and work some more problems and get you comfortable with that. What if you had y squared plus y is equal to 1 plus x over 1 minus x. So here is an equation, and what we want to find is dy dx, the first derivative, but y is not solved for by itself. This is not explicitly defined. This is an implicit function. In other words, we know how y and x are related, but we don't have y on one side of the equal sign by itself. So the way we do that is we take the derivative of both sides. Now on the right hand side, it's going to be exactly what you've been doing up until now. In this case, it's the quotient rule. Bottom times the derivative of the top minus the top times the derivative of the bottom squared. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom all over bottom squared. Okay, so when you see x's, I guess is what I'm trying to get at, in these implicit functions, you just take the derivative of those x's just like you always have. No difference. But when you have the y's, there's a little bit more that you have to do here. The derivative of this first term is 2y, all right, just like if it were x, but you have to multiply by dy dx because you don't know how y varies with respect to x. That takes care of this term. The second term, the derivative of this is just simply 1. But again, you have to multiply by dy dx because you don't know how y varies with respect to x. So if you don't understand anything else, the way you handle implicit differentiation is you take the derivative of the y's just like you always have, except you tag a dy dx onto there, always. And then the x's, you take derivatives exactly the way you've always been doing for everything up until this point. And that is really the short, dirty little secret in how you handle it. So let's factor this guy out. We'll have a dy dx. And on the inside, we'll have a 2y plus 1. The reason we're factoring it out is because we want to solve for dy dx. That's what we're trying to find. And on the right-hand side, we'll have 1 minus x. The derivative of this guy is just going to be 1 minus 1 plus x. The derivative of this guy is negative 1. And on the bottom, we're just going to have 1 minus x squared. So let's go ahead and simplify this just a little bit more. We'll have dy dx, 2y plus 1, and then over here it'll be simply 1 minus x. Here we're going to distribute in negative times negative is positive, so we're going to have 1 plus x just sitting on the top, and then we'll have 1 minus x squared. So we just have to simply have some algebra. So just to continue simplifying, what we'll have is dy dx, 2y plus 1. On the top, negative x goes out with x, so what we'll have is 2 over 1 minus x squared. So to finish this guy up, we'll just solve for dy dx. And we're dividing here, so what we're going to have is 2 over 2y plus 1, 1 minus x squared. And that's the answer. 2 over 1 minus x squared times 2y plus 1, which is exactly the answer. Now notice that this is the derivative of y with respect to x. In order to actually calculate a value, a numerical value for the slope of our original curve, which is a derivative, we'll have to supply a x and a y point, x comma y, a point on this relation, on this function. We can't really graph it so easily because we don't have y defined in terms of x, but certainly there are values of x and y that go together that would make this equation valid, right? So there are ordered pairs, x comma y, that fit this function. We just have to supply one of them to calculate the slope of the original curve at that function. So it's very common when you get your implicit differentiation, your implicit derivatives, to have y's and x's running around your answer. And the reason that's the case is because our original function was not explicitly defined. So our derivative is not going to look quite so nice either. That's basically the bottom line on that. Let's say you're going to find the secant of y minus the tangent of x is equal to 0. We want to find dy dx. We want to find the first derivative. It's a great example. You can't really solve for y. I mean, you could pull tangent over there. You could take the inverse secant, but then you have to take the derivative of all of that stuff. You don't know how to do that. So you can't do that. So what we're going to do is use implicit differentiation. We're going to take the derivative of each term separately. What is the derivative of the secant function? Derivative of secant is tangent secant. So you just take the derivative normally, tangent y secant y. But since we're dealing with y, we have to multiply by dy dx because we don't know how y varies with respect to x. This is kind of like the chain rule. We take the derivative of the outer function times the derivative of the inner function. But we don't know what dy dx is, so we just write it like that, right? Next, derivative of tangent is secant squared. Secant squared x, that's it, and then we have equal 0. All right, so then all we do is solve for dy dx. dy dx is equal to, we move secant squared over there, so positive secant squared x, and on the bottom we write tangent y secant y. And that's the answer. Now notice we cannot cancel this secant with this secant because this is secant of x, secant squared of x, this is secant of y, totally different variables. So if we wanted to find a value of the slope of this curve, we'd have to supply a value of x comma y at that spot to be able to do that. Okay? Now let's say we have the function sine of y over y squared plus 1 equals 3x. Okay? So again, you can't really solve for y here. You've got sine of y, and then you have y squared plus 1. It's just impossible to really solve for that very easily. So we're going to take the derivative of both sides. On the left, we take the derivative using the quotient rule. Bottom times the derivative of the top, y squared plus 1, times the derivative of the top. So what I'm going to have is sine y prime, bottom times the derivative of the top, minus the top times the derivative of the bottom, y squared plus 1, derivative of the bottom, over bottom squared. So it's going to be y squared plus 1 squared. Just leave it like that for now. Okay, and on the right-hand side, we'll take this derivative of 3x, which is just simply 3. That's quite simple. So we haven't actually taken any derivatives on the left-hand side yet, so let's go ahead and do that now. We'll have y squared plus 1. What's the derivative of sine? It's just cosine. So we'll have cosine of y. We can't stop there, cosine y, but we have to write dy dx. This is like the chain rule. We take the derivative of sine getting cosine, but then we have to take the derivative of the inside, giving us dy dx, because we don't know how y varies with respect to x. Minus sine of y. Then over here, we take the derivative of this guy. We take the derivative of this, giving us 2y. The derivative of this is 0, but we can't stop there. We have to multiply by dy dx. Because we take the derivative of this term, but we don't know how y varies, so we have to write dy dx. On the bottom, we don't have any derivative, so we just say y squared plus 1 squared. And on the right-hand side, we just say we have 3. Okay. Now let's clean this up a little bit. So what I want to do is pull this dy dx out. Let's factor it out, so to speak. So what we'll have is dy dx on the outside of this whole thing. Let's write it like this. Let's keep the fraction intact. On the top, what we're going to have is the same thing we've had to begin with. We'll have y squared plus 1 times, take away those parentheses. We don't need as many parentheses. Cosine of y, that's what we have on the top here. And then over here we'll have minus 2y sine of y. Close the brackets off. And then on the bottom, we'll go ahead and write it as y squared plus 1 squared, and that'll be equal to 3. Okay, now you see why we've written it this way. Notice that this is exactly the same thing. We just take the dy dx, we pull it out here. If we distribute it back in, we get exactly what we were left with before. The reason we do it this way, pulling it out, factoring it out, is because we want to solve for this. So let's go ahead and move all of this business over here. The way we're going to end up doing that is by multiplying by the denominator to get it over here. It'll cancel on the left. We'll divide the top to get it over there. So what we'll have at the end of the day, we can just write our final answer. dy dx is equal to 3y squared plus 1 squared over, and what we'll have here is cosine y squared plus 1 minus 2y sine y, and that's the answer. So we'll have 3y squared plus 1 squared cosine y squared plus 1 minus 2y sine y. Notice the final answer has y's and in this case doesn't have any x's in it. That's okay. It just depends on the function that you're given. Sometimes you're going to have x's and y's in your answer. Sometimes you're just going to have y's. But basically you just run with what you're given. So if you needed to find the derivative of this function as it relates to x, you could just put any value of y you wanted into here, and it will give you dy with respect to x. The reason the x dropped out is because the x component of our original equation was so simple that when we started taking derivative, it just fell out. All right, but we treat it exactly the same way. Bottom times the derivative of the top minus top times the derivative of the bottom over the bottom squared. We do all the same rules. Once we take this derivative of sine is cosine, we have to multiply by dy dx because that's the derivative of sort of our inner variable here. Here we're doing the same thing. Derivative of this is 2y dy dx. Follows the same pattern when you're doing implicit differentiation. When you're taking the derivative of the x's, you do it exactly as before. When you take the derivative of the y's, you do it exactly as before, but you have to tag a dy dx onto there. And then you solve for dy dx to get your final answer. Okay, our next problem is, what if we have x squared plus x squared y squared plus y cubed is equal to 3? Okay, can't really solve for y easily anyway because you've got it wrapped up with these exponents in two different places. So we'll use implicit differentiation. We'll go term by term. On the left-hand side, take the derivative of x squared. We're just simply going to get 2x. That's just like before, so we don't do anything different. Plus. Now when we get to this term, we have x squared y squared. This is two functions multiplied together, so we have to use the product rule. So what it's going to be is the first function times the derivative of the second function plus the second function times the derivative of the first function. We'll leave that job for later. And then finally we take the derivative of this, y to the third power, and we'll have 3y squared times dy dx. Anytime we're dealing with the y's, we just tag a dy dx after we take the derivative. On the right-hand side, derivative of 3 is 0. So let's go and tackle what we have in here. You'll find out it's not too bad. 2x plus. On the outside here, what we have is x squared. Here we have 2y, taking this derivative, 2y, but we have to tag a dy dx because we're dealing with the y variable. So we have to see how y varies with respect to x. So x squared comes down, 2y comes from here, dy dx, plus y squared is just rewritten. And then here, derivative of x squared is 2x. And that's it. We're dealing with an x there, so we don't have to tag anything on the end of it. Plus 3y squared dy dx is equal to 0. So let's tidy this guy up and figure out what we have. So what we have here is 2x plus 2x squared y dy dx plus 2xy squared plus 3y squared dy dx. Now ultimately what we want to do is to be able to solve for dy dx. So what we need to do is move all of the terms that don't involve a derivative over to the right-hand side. So let's do that. So over here we'll have 2x squared y dy dx. We'll keep this term on the left-hand side, 3y squared dy dx. And what we'll do is move this term and this term over by subtracting them. Negative 2x minus 2xy squared. So all we did was move those over. Now on the left, in order to solve for this, we're going to have to factor this out. So we'll say dy dx And on the inside, we'll have 2x squared y plus 3y squared is equal to negative, well, let's factor out a 2x here, 2x, 1 plus y squared. You should be able to convince yourself this is exactly what this is. Factor the 2x out, you're going to have the 1 plus the y squared is the only thing left over. All right? And the final answer can be written next, dy dx. We just divide by this whole term to get it by itself. So we'll have negative 2x, 1 plus y squared, and on the bottom, we'll have this guy, 2x squared y plus 3y squared. So we'll have negative 2x, 1 plus y squared, 2x squared y plus 3y squared. And that's the final answer. Notice our derivative has x's and y's in it. So if I wanted to find the slope of the line tangent to our original curve at a point, x comma y, I'd have to supply x comma y into this guy. It would calculate a number that would be the slope of the line tangent. The reason that we have x's and y's running around in our derivative is because we do not have our original function explicitly solved for y. And that's the main difference. So I could stop here and just say, you know, congrats, you understand implicit differentiation. But what I'd like to do now is go ahead and close this section, let you digest what we've learned, practice these problems if you need to, and I really encourage you all to do that. In the next section, we'll just work a few more problems. They'll be a little bit more involved, just to give you a little bit more practice with some more complicated problems, but the process is exactly the same. I give you a little bit of a lecture at the beginning on what implicit differentiation is, why do we need to use it, but the bottom line is anytime you have a relation that doesn't have y explicitly solved for it in terms of x on the other side of the equal sign, then we have to use implicit differentiation to get the derivative. We take the derivative of both sides. Anytime we run into x's, like we did here, we just take the derivative normally. That's all we do. Right? Whenever we run into y's, we have to take the derivative normally, but we have to tag it by multiplying by dy dx. And that comes about because of the chain rule. Because we're taking the derivative of this outer guy, we're taking the derivative of the inner, giving us dy dx. Now, I'll say one more time what I said earlier. You're doing the same thing when you take the derivative of this as well. You're using the chain rule also, it's just you didn't notice it. You take the derivative of the outer function giving you 2x, but you're always multiplying by the derivative of your variable. In this case, it's x. So you would be multiplying by dx with respect to x, dx over dx, which is 1. So that's why in all these derivatives up till now, you've never seen dx dx, dx over dx, dx over dx, and all these terms, because it's not usually taught that way in calculus because you don't ever really see it. So when we take this guy, we teach you, just do it this way, 2x, not to write dx dx. But I'm taking the point to tell you that now because, so it doesn't seem so weird why you're doing it for y. In this case, when you do this guy, you're taking 2y dy dx because you don't know how y varies with respect to x. When you're dealing with an x variable, how does x vary with respect to x? It's the same variable, so it's 1. So you don't ever see that. But practically speaking, when you see x's, take your derivatives normally. When you see y's, take your derivatives normally, but tag it with a dy dx. That comes from the chain rule. That's how you do implicit differentiation.